They have a lone pair of electrons, but they don't like have a full negative charge or anything. There are a lot of reagents in organic chemistry. If you don't have some kind of organizational strategy, they're going to get overwhelming. You're not going to remember what reagent does what in what kind of reaction. Having a good organization strategy is a key to being a true OChem ninja. One of the ways you can do that is by going back through your notes and organizing all the nucleophiles and bases into various categories. I'm going to help you with that today. This isn't a video on how to find and identify nucleophiles and electrophiles. I have a separate link to that video down below. The first category is what I like to call good, strong anionic nucleophiles, GSANs. These nucleophiles have a lot of inherent energy, a lot of electron density packed into a very small volume. That makes them very good, strong anionic nucleophiles that can get out there and directly attack electrophiles to do some kind of reaction. These types of nucleophiles are good for acid-base reactions along with SN2 reactions. They can do an E2 reaction if they're a strong enough base as well, and carbonyl additions. So what are the good, strong anionic nucleophiles? Some of the good, strong anionic nucleophiles include hydroxide, where the oxygen is the nucleophilic atom. In general, any alkoxide is a good, strong anionic nucleophile. A negatively charged oxygen is a good, strong anionic nucleophile. Same thing with the sulfur variants as well. HS- and generic RS- are also good, strong anionic nucleophiles. The cyanide anion and the azide anion are also good, strong anionic nucleophiles. Also Grignard reagents, alkyne anions, enolates, hydride reductants like lithium aluminum hydride, and even reagents like X-, although X- a generic halide anion is not strong enough to do an E2 reaction. All of these reagents have some kind of element in them that have a lot of excess electron density, a high concentration of electron density that makes them good, strong anionic nucleophiles able to directly attack things. There's two more that I'm going to put on my list, but I'm going to put them in parentheses. They're not my favorite of good, strong anionic nucleophiles. And that is neutral ammonia and also generically any neutral amine. These have a nitrogen atom that has a lone pair and is a strong nucleophile. It's not very synthetically useful though. It has some side reactions that get in the way of trying to do things like SN2 reactions. So I'm going to put them in parentheses even though they are good, strong nucleophiles. The next class of nucleophiles I call weak neutral nucleophiles, WNN. These are nucleophiles. They have a lone pair of electrons. They have excess electron density, but they don't like have a full negative charge or anything. So they're not good, strong anionic nucleophiles. On this list would be things like neutral water and really any neutral alcohol. Notice the difference between OH- and H2O and RO- and ROH. They're essentially the same reagent. One is anionic, one is neutral. That goes also for the neutral versions of the sulfur reagents. These are neutral reagents that have lone pairs on sulfur, but not like a full negative charge or anything. The last reagent I'm going to add to this list may surprise you, and that is a carboxylate. A carboxylate with a negative charge, the conjugate base of a carboxylic acid. Why is this a weak neutral nucleophile? It's clearly anionic. Well, this negative charge can be stabilized with resonance with the carbonyl, so that negative charge is spread out over a larger volume, which makes it a weaker nucleophile than you would otherwise expect. This really does more of the weaker nucleophile type reactions than the good, strong anionic nucleophile type reactions. The last category to talk about are what I call non-nucleophilic bases, NNBs. These are nucleophiles that aren't very good nucleophiles. They're much better at being bases for some reason, either a steric reason or an electronic reason, but these are non-nucleophilic bases. They do base things, they don't do nucleophile things. So they do acid-base reactions and E2 reactions. The common examples here is something like sodium hydride. Sodium hydride, the H- here is a good strong base, but not actually quite a good nucleophile. The prototypical molecule in this category is potassium T-butoxide. This is the generic non-nucleophilic base, the prototypical one that we think of probably most often. In general, any deprotonated amine is also going to be a non-nucleophilic base. The most common examples of that are H2N, we often see that as NaNH2, or LDA, which is lithium diisopropyl amide, with two isopropyl groups on either side of the nitrogen. The last base I'll include in this category is DBU. It's a 7-atom ring next to a 6-atom ring. I've got a separate video down below on getting good at drawing these different sized rings. This is more of an exotic base. We don't necessarily see it all the time. You may not even see it in your course at all, but if you do, this is the structure of DBU, and it's a non-nucleophilic base. An OChem Ninja would have this list at hand at all times and add to it as you go throughout the course. When you're doing practice problems or studying for an exam, when you get to a new reagent, you want to look at that reagent, see if you can classify it as a good strong anionic nucleophile, a weak neutral nucleophile, or a non-nucleophilic base, because that's going to give you some key information about how this reagent is going to be working in this particular mechanism.
Thanks for training with us today, Ninjas. Check out this other content to see if you can level up even further. As always, don't forget to like and subscribe.